Continuing our discussion of basic dynamics, velocity, displacement and acceleration, let's move on and talk about systems that are under motion but with constant acceleration. So for any object, be it a car, ball, subatomic particle, anything we'll deal with in this class, any object with constant acceleration will be subject to some delta v. A delta v, remember, being a change in velocity or acceleration a. So in this case, we have an object moving in the x-axis with some velocity vx. That means its velocity will be whatever its initial velocity is that's imparted to it, plus some change in the velocity. So if a vehicle is moving at 10 meters per second, and then it's subject to an acceleration, a delta v, it will then change to adopt the new velocity, a total of delta v plus whatever original velocity it had. This delta v happens to be an acceleration in the same axis. So if we're moving in the x-axis, we can couple our velocity with an acceleration in that axis. And how long is that acceleration applied for? How long is the speed changing? So we can say v is going to be v0 or vi in some cases, an initial velocity, plus delta v is going to equal our original velocity plus the acceleration times how long that acceleration is applied. So a particle that's under constant acceleration with some x velocity at some initial time will speed up to say that its final velocity will be v, being initial velocity v0 plus at. Now, when we deal with a system of constant acceleration, that does not mean constant velocity, and that is a very common error. It means that the change in velocity with time is constant if we say constant acceleration. That means, as we said before, we can plot a VT graph and look at the ratio of dv to dt. So here is our velocity time graph in the x-axis, here is the change in time, here is the change in velocity. And as we saw with our displacement graph giving us velocity, a VT graph, a velocity time graph, its slope will give us acceleration. Or, put more succinctly in calculus terms, the acceleration is the first differential of velocity, dv by dt, or the second differential of position, d squared x by dt squared. So being given a position function, you could differentiate twice and get acceleration. Given a velocity function, you could differentiate once and get an acceleration. So remember, in most cases, a nice straight line VT graph may be unusual. You may see a whole variety of VT graphs of different forms, depending on how the acceleration is varying. Now, if we take acceleration graphs or VT graphs and look at the area beneath, i.e. apply integration to these particular curves, what we can do is end up with 5 fundamental relations, which I will give to you shortly, between displacement, velocity, and acceleration for any recorded time. So what I'm saying here is, in some cases, reinventing the system and coming out with brand new relations all the time is not always necessary. These are going to be referred to as our equations of motion. So the area under a VT graph gives the displacement of your particle. And that should make sense, really, because displacement is going to be an integral of VT. It's going to be an integral of your velocity function with respect to time. And likewise, the velocity is going to be an integral of an acceleration function. So it really depends what you have. If you have a velocity function and want displacement, you can integrate. If you have a velocity function and want acceleration, you can differentiate, and vice versa, depending what you have. But analysis of these curves and looking at the calculus of various constant acceleration systems give us what are referred to as the equations of motion. So if we look at the basic motion of any particle, we can take it down to 5 basic variables: v, I, vf, a, s, and t. Initial and final velocities, acceleration, displacement, and time. Those 4 equations can be used to find any other value. These are going to be referred to as the equations of motion, and these are the equations you really want to keep in mind as the starting point for our discussion of dynamics for the entire semester. When we start to talk about forces later on, you'll often have to find acceleration. When we talk about momentum later on in the course, you'll have to come back to these equations to find v to calculate p equals mv. So don't just look at these equations, feel like you need to use these equations to pass an exam soon, and then forget about them. These are going to be the foundation of everything else that we're going to do. And later on, we're going to take it for granted that you can go back to these equations should you need to. So I would say learn these now and learn them well and how to use them, or more precisely, where to use them. And knowing which equation to use in which situation takes practice. And I would encourage you to look through the book, take the examples from the chapter, and work through those examples. And don't say to yourself, what's the final answer? Look at the problem itself, read it through, and ask why was a specific equation of motion chosen. We're not worried about the final answer being 12 meters a second, or whatever the answer is. Worry more about why did the author of the book select this particular equation. And that's kind of what you want to think about as we go through these slides. But our equations of motion, these 4 basic equations, are right here. The first is one we've already seen in our previous slides. Vf here is equal to Vi plus At. S, displacement, is equal to 1/2 Vi plus Vf times t, essentially an average of 2 velocities times time. 3 and 4 tend to be the ones that I would refer to the most. 3, S equals Vit plus half At squared. And finally, Vf squared is equal to Vi squared plus 2As. And remember, S can be a displacement in either x or y directions, or even z sometimes, depending on the situation. So let's take a look at how we can employ these equations. So if we look at a bullet being fired from a gun that has a 15.2 centimeter long barrel, it attains a muzzle velocity of 330 meters per second. Now, a key point in this question is it saying assume constant acceleration. That is a pointer. That is a hint saying use the equations of motion. It doesn't quite say use the equations of motion. It says assume constant acceleration. It's telling you it's a constant acceleration system, so the equations of motion are valid. It's leading you towards the methods you need to use. Back to the question. How long does it take the bullet to travel down the barrel? Well, a muzzle velocity is the velocity that a bullet has as it leaves the gun barrel. So we're going to have a velocity here of 330 meters per second to play with, and we're going to have a displacement down the barrel of 15.2 centimeters. So read through the question carefully and decide what do I have and what do I need, and then create a shopping list. And initially, this list should look something like this. Vi is equal to 0. That's the initial velocity. So a bullet will start from 0 in its chamber, and as it's fired, as it leaves the barrel, it'll reach 330 meters per second. So Vf is 330. S is 15.2 centimeters. Now, a key point here that should be made obvious is that S is in 15.2 centimeters, VF is in 330 meters per second. And a common error, especially on exams when people are in a hurry, is that these two units are incompatible. They're out by a factor of 100. So you will have to change centimeters to meters in order to use it in the equation with meters per second. And the preference here is to do everything in meters and seconds. Please don't convert everything to centimeters. But we want to find T and convert to meters along the way. If we want to find T, we have S, we have VI, we have VF. We can substitute in for these. Here you can see I've taken the 15.2 centimeters and converted it to 0.152 meters. This is equal to 1/2, 0 being VI, 330 being VF, times T. Rearranging, T will therefore become 2 times S over VI plus VF. Substitute in, T is 0.152 times 0.152 over 330, which will give us 9.21 times 10 to the minus 4 seconds. That is a very small number. But we have to ask ourselves at the end of every problem, is that a reasonable value? And yes, it is. Here we're looking at a 15.2 centimeter distance being covered at 330 meters per second. That is quite a reasonable value, even though it's a very small number. Let's take another look at another problem. Here we have an electron that's being accelerated in a particle accelerator. The electron is going to accelerate from a speed of 3 times 10 to the 4 meters per second to 5 times 10 to the 6 meters per second over a distance of 2 centimeters. Now I want to point something out here. When we're dealing with these very high rates of speed, these very high velocities, you can never exceed the value of about 3 times 10 to the 8 or 2.99 times 10 to the 8 meters per second. That is the speed of light. If somehow you discover that something can travel faster than the speed of light, please bring the proof to me. I will take it, read it very carefully, and being the professor that I am, probably borrow it a little bit and put it into a paper and make us all very famous and get us all Nobel Prizes. Nothing should actually exceed the speed of light. So if you find yourself calculating something with a value of 3 times 10 to the 8 or more, then, well, in terms of velocity anyway, then you're probably wrong. But anyway, back to our problem. An electron's accelerated. It goes from 3 times 10 to the 4 meters per second to 5 times 10 to the 6 meters per second over a distance of 2 centimeters. That is going up 2 orders of magnitude from 10 to the 4 to 10 to the 6 over 2 centimeters. These numbers are going to be quite large, quite extreme. We've got 2 questions. A, how long does it take the electron to reach this speed? And B, what's the acceleration? So again, this is a case of selecting the right equation. What do we have? Well, we have a VI of 3 times 10 to the 4, a VF of 5 times 10 to the 6, and a displacement of 2 centimeters. How long? Same procedure we saw before. Don't be afraid to reuse an equation. There's only so many equations, and they will be repeated a lot. So S is 1/2 VI plus VF times T. T becomes 2S over VI plus VF. We have our values. Let's sub them in. 2 times 2 times 10 to the minus 2, that's our centimeters, divided by 3 times 10 to the 4 plus 5 times 10 to the 6, gives us 7.95 times 10 to the minus 9 seconds. That's a tiny fraction of a second, but given the speeds we're traveling and the short distance that we're moving over, that's a reasonable value. The most common wrong answer here is people forgetting to do the centimeters here and convert the 2 into 2 centimeters. And the most common wrong answer gives us 4 over the 3 times 10 to the 4 plus 5 times 10 to the 6, which gives us a factor of 7.95 times 10 to the minus 7 seconds. So out by a factor of 100. Please be careful not to make this kind of error. There's a reason I point it out, because people often do. Part B, what is the acceleration of the electron? Now I really want you to think about this, because as you look at this problem, what frequently happens is people pull up their equations of motion and look at the equations of motion and study them and think very, very hard about them. But something else you shouldn't be afraid to do is really think about the fundamental values. Is there a point in using an equation of motion here and rearranging it when you can just use the fundamental value, fundamental definition even, of the acceleration? And what I'm saying here is we have 3 times 10 to the 4, 5 times 10 to the 6 meters per second, and now we're armed with a time of 7.95 times 10 to the minus 9 seconds from part A. That means rather than going back and employing an equation of motion and making your life complicated, you could simply use the definition of acceleration, because A is delta V over delta T. That means we have VF, we have VI of 5 times 10 to the 6 and 3 times 10 to the 4, and we have our time of 7.95 times 10 to the minus 9 seconds. That will give us 6.25 times 10 to the 14 meters per second per second. Now I realize that's an enormous value, 10 to the 14, and earlier on I said that velocity could not exceed 3 times 10 to the 8. That's because this isn't a velocity. This is an acceleration, which can take pretty much any value, because this is an increase in speed and not a speed or velocity in and of itself. So let's take another look at some of the calculus problems that we already looked at. Earlier on, we had a particle moving along the x-axis. Its x-coordinate varied with time by x equals negative 4t plus 2t squared. We were asked to determine the displacement of the particle from 0 to 1 second and 1 to 3, find the average velocity over the 0 to 1 and 1 to 3 second interval, and the instantaneous velocity at a point. So we saw this graph previously, and we're just kind of recapping this in light of things we've already done. Our function is x is equal to negative 4t plus 2t squared. Remember, this is a displacement. So what we can say is from t equals 0 to t equals 1 second, x is equal to 4t plus 2t squared. Our displacement is going to be xf minus xi. We can therefore use our relation twice and say that 4 times 1 plus 2 times 1 squared minus 4 times 0 plus 2 times 0 squared. Of course, if you're doing this on an assignment or exam, I wouldn't expect you to show this extra step with all these zeros in. I'm just putting this in for completeness. Will give us negative 2 meters. There's actually no application of calculus here, just applying the function. What's the displacement of the particle now? From 1 to 3 seconds. Well, our displacement from 1 to 3 is xf minus xi again. Substituting 3 here. Substituting 1. So 4 times 3 plus 2 times 3 squared minus 4 times 1 plus 2 times 1 squared will give you plus 8 meters. There is also a faster way of doing this, and that is you could just read x straight off the graph. Part B says find the average velocity from 0 to 1 second and 1 to 3 seconds. Well, in the first time interval, we can say delta t is tf minus ti, which is 1 second. And we can say v is delta x by delta t. This is going to be minus 2 over 1. This will give us negative 2 meters per second. v13, the second time interval, will be 8 over 2, which will give us 4 meters per second. Those are basically the slopes straight off of the graphs. So you could have just quoted the slopes, but here we showed the same thing in an algebraic sense. For part C, if we're looking at the instantaneous velocity of the particle at t equals 2.5 seconds, well, the slope of the xt graph is going to give you 6 meters per second at t equals 2.5. So you can come over here to t equals 2.5 and you can look at that from the graph. Or if we were to do this using calculus, we'd say v was dx by dt. This would equal d by dt of negative 4t plus 2t squared. If we calculate this out, we'll get negative 4t plus 4t. Factor out the 4. I realize that you could essentially bring this to 0 if you decided to do so. That would be foolish because then we wouldn't have an actual function. This will be 4 times negative 1 plus t. So at t equals 2.5 seconds, we'll end up with a substitution 4 times negative 1 plus 2.5 would give 6 meters per second. So let's look at a few more applications of the equations of motion. Let's take a look at a rocket. And in this case, it's a rocket that's going to move up from rest with an acceleration of 29.4 meters per second. This rocket is going to run out of fuel after 4 seconds, but it's going to continue to coast upwards. That means it's going to keep moving upwards without an acceleration being applied to it from the rocket engines. It's then going to reach some maximum altitude. Gravity will have taken away all of its velocity, and then it will fall back to the Earth. So what we're saying is here's the rocket. I'm going to call this phase 1. The rocket's going to move upwards with an acceleration of 29.4 meters per second. Now, when this acceleration is mentioned, when this acceleration is actually quoted, this should be taken as the overall acceleration on the vehicle. There's no need to go subtracting gravity from this. So it moves up with 29.4 meters per second, and its fuel burns out after 4 seconds of motion. The rocket's going to continue upwards in what I call phase 2 until it reaches some maximum height. At that height, it's got to turn round and come back down. So something to remember over the entire time this rocket is moving is there is an acceleration of negative 9.8 from gravity acting downwards. That means the moment that the rocket engines are turned off and the upwards acceleration has ceased, that gravity is taking velocity away from this rocket. That means the old adage of what goes up must come down, unless you put it into orbit, of course, means that this rocket will go up, hit some maximum height, and then it'll turn around and come back down. Hopefully not crashing into the floor in a ball of fire. So that's a situation you have to take into account, and that's the situation that's being explained in this problem. So the questions are, what is the rocket's position and velocity after 4 seconds? And remember, after 4 seconds is when the acceleration from the engine stops. And then, what's the maximum height of the rocket? So, what do we have to play with? We have an acceleration and we have a time. We can say VF is going to be VI plus AT. The other equation we might be tempted to use is S is equal to delta Y, essentially in this case, because we don't care if the rocket went in a parabolic arc. We don't care what it's doing in the X direction. We're only analyzing this rocket in the Y direction. So S for our purposes is VIT plus half AT squared. Our acceleration is going to be 29.4 meters per second. Our initial velocity for phase 1, this rocket starts out on the ground and then takes off. So its initial velocity is 0, its initial position is 0. But we know it travels for 4 seconds. So VF is going to be VI plus AT. where our initial velocity is 0. This means v is essentially equal to at, which is a definition you could know without even employing the equation of motion if you wished. And that's going to be 29.4 meters per second times 4 seconds. That will give us 117.6 meters per second. So this is the velocity that the rocket is traveling at the end of phase 1, when its engines burn out after 4 seconds. Now, we have v. Now we can say y is equal to vit plus half at squared. So now we're tackling part B of this problem. Vi was 0, so this is half at squared now, and we can plug in our 4 seconds here and say this is half 29.4 times 4 squared, which is 235 meters. So this is the height that the rocket was at after 4 seconds. This is not the maximum height of the rocket. This is the height of the rocket here at the end of phase 1. So, what is the rocket's position and velocity after 4 seconds? It's traveling at nearly 118 meters a second, and it's sitting at 235 meters up. You had to use 2 separate equations of motion to get those 2 answers. You could not use one equation as some magic bullet to get both. So the next question is, what is the maximum height reached by the rocket? What do we know about this? Well, what we know about this is at maximum altitude, the rocket has to turn around and come back towards the Earth. At a turning point, the velocity of the rocket must be 0. So what we can say is at maximum altitude, the velocity of the rocket is nothing. That means we can employ the following equations. V would be equal to AT plus our VI plus AT. So this is our initial velocity. I turn them around. This is our initial velocity. And the reason I turned it around is I wanted to show acceleration G of 9.8 meters per second. This is the acceleration due to gravity, and is the one fundamental value that everyone in this class should know that won't be provided on any formula sheets. This is the most basic value in all of mechanics. So V is basically VI plus AT. Our displacement is going to be 235 meters, that is our altitude from part 1, plus 118 times t, so this is Vt, and this is half At squared. Why is it half? This is 4.9 meters per second. This is 9.8 divided by 2. Why are we using g here? Well, the engines were switched off. The only acceleration that was acting on this system after the engines were switched off was the acceleration due to gravity down towards the Earth. Hence the fact these negative values have now been applied, telling us the direction of that acceleration. This is half At squared already, so this is 9.8 over 2. Why do we have 2 equations? Well, we can't do anything without t in equation 2. So we need to find t. We need to find time. So using equation 1, we can get t. Here we're going to say that 0, which is our velocity at maximum altitude, which is v, is going to be negative 9.8 times t plus 118. This is vi plus at. So t, if we rearrange, will give us 118 over 9.8, which will give us 12 seconds of flight time to get to maximum altitude. Now, since we're armed with t, let's take t and stick it back into the second equation. So using equation 2, we can now say that we're going to take our 235 meters that we reached in phase 1 plus 118 times 12 that we just derived, minus 4.9, this is half a, half g essentially, times t being 12 squared, which will give us 945 meters. The most common error here is the question is asking what is the maximum height reached by the rocket? Well, this whole part here is a calculation of the height attained after the engines are off. This is the height attained before the engine's switched off. So it needs to be added on to get the total altitude. So before we're done, we want to take a look at some graphs. As I said, the fundamental relationships that we're looking at, V, A, and S, are all related by calculus and by studies of various S, V, and T graphs. So let's take a look at our velocities and accelerations and how these quantities vary with time. So here we're playing the Ghostbusters car Ecto 1 is playing a role. As this vehicle moves, we can chart its motion as it moves from left to right. After 1 second, this vehicle has gone 10 meters. After 2 seconds, 20, 3, 30, 4, 40, 5, 50, blah, 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 if this continues. That seems like a relatively simple relationship, because it is. What we're really seeing here is every second this vehicle has gone another 10 meters. So it's not particularly difficult to ascertain that this vehicle is moving at 10 meters per second. So here we have 6 different data points. This means our velocity was constant with time. The velocity was not increasing. That means the car was not accelerating. If we were to plot a VT graph, you should really know the form of a graph like this. Our velocity time, VT graph, with no acceleration will look like this, with this nice flat line sitting at exactly 10 meters per second. Velocity here is constant with time. Now the question you need to ask yourself is what would the displacement time displacement time graph, that relates to this VT graph look like? So if we are given his VT graph, what does displacement time look like? Well, the displacement with time was steadily increasing. Every second, this vehicle had gained another 10 meters. So here we have distance, our displacement. Here we have time. The corresponding dt graph or st graph to that velocity time graph will look like this. Every second, the vehicle gained another 10 meters. And it's this kind of relationship of being able to look at an st graph and know that its VT graph looks like this, or look at a VT graph and know what its ST graph will look like. That's the important discipline I'm trying to show here. So take the same situation, but now the vehicle is accelerating. It starts off at an S of 0 at 0 seconds. After 1 second, it's gone 2 meters. 2 seconds, it's gone 8, 3, 18, 4, 32 meters. 5 seconds, finally, it's still 50 meters, but its gain speed, its velocity here has changed and is no longer uniform. This is not a uniform velocity. This means the velocity is increasing with time, so the system is accelerating. Now, this is a system of constant acceleration. A system of constant acceleration will have a VT graph which will follow this kind of relationship. Here's our velocity, here's time. After 1 second it's at 10, 2 seconds it's 20, 30, blah, blah, blah. We will end up with a straight line. That is a system of constant acceleration. So that's what you really want to think about. These words, these terms are very similar. A constant velocity system would have no acceleration. A constant acceleration system will have a steadily increasing velocity. So the terminology is very fine there, but please make sure you can understand this and really read it carefully before you make any determinations about ST, VT, or AT graphs. So here, the acceleration is constant because this vehicle is gaining the same amount of speed every second, but the velocity is not constant. And we can see whole families of graphs. And there's no need to memorize every single version of a graph. Just realize what's going on. What's constant? What happens if something's decreasing? What happens if something's increasing? So in this particular case, here's our velocity increasing. Our displacement graph will take a t-squared relationship. Here's a situation we saw at the beginning of this particular section on graphs with a v which is flat. If v is flat, there's no acceleration. This is a constant velocity. So this particular case here, this has an acceleration. It's just a flat line here at 0. If you were to actually see this on an exam or something like that, you rather than trying to draw it in, you just have to write 0 acceleration. In the same way, in this case, as velocity was increasing steadily, the acceleration here was constant and was a flat line for this one. The most common error here is people draw a VT graph and a corresponding increasing AT graph. The acceleration is constant, the velocity is changing. This I consider the simplest. X of t is just increasing, velocity is flat, no acceleration. And in the final case, it's really the first case flipped upon its head. Here is displacement, moving in a negative squared pattern. Velocity will therefore be going down, decreasing. This is a negative acceleration case, a deceleration as you'd call it in everyday life. Now, that does not mean that the acceleration takes a negative slope. The acceleration is constant, as it was in the first case. It's just in the negative axis. And there's just another slide showing you the same kinds of relationships, just here saying explicitly that v is 0, displacement, velocity, and acceleration will be this. The velocity is 0. The object is not moving. It's sitting at some value of x constantly. So these are the kind of interpretation you really want from your graphs. Motion with constant velocity, we just saw, constant acceleration, and a constant, they've used the word here, deceleration. So you can take a look at a few graphs here. If we have a VT graph of this form, what will the corresponding AT and ST graphs look like? Now, I haven't gone as far as putting music on here. Suppose I could hum the Jeopardy theme or something like that and sit here going da 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 da. Yeah, I can't be bothered. So this is our VT graph, velocity versus time. What will our ST graph look like? It'll be in a squared form. S squared versus t. What will our AT graph look like? Nice flat line. Hope you guessed that correctly. Here's an AT graph, starting out with acceleration time here. And this, you should note, is down here in the negative axis. This is a deceleration or a negative acceleration. That should mean you'll see a negative slope in the VT graph. The corresponding displacement time graph will have a negative S squared relationship. Here we go. So there's that same set of graphs that we saw previously, just here on the same slide, just in white instead of black. I would definitely take a look at these, realize what corresponding values look like. How does V look in relation to X? How does A look in relation to V? And how do these families of graphs vary? So let's take a look at a few more examples. In this case, a secret agent is driving his car through a school zone at 80 kilometers per hour. A henchman on a bike is going to take off in pursuit of him the moment the car passes him. The bike is going to accelerate constantly at 8 meters per second per second. Now, it says accelerate constantly. That means it's leading you to a constant acceleration system, which is practically pointing towards the equations of motion. So, part A asks how much time will pass until the bike is traveling the same speed as the car. So how long will it take the bike to reach 80 kilometers per hour? Part B says how far is the bike from the car when it reaches this speed. There's the car moving past the bike and the bike starting up as the car passes it. So what we have is a velocity of the car, an acceleration of the bike. We want to know how much time will pass until the bike's traveling the same speed as the car. So we can say that A is delta V by delta T. That means T is going to be V over A. We have 80 kilometers per hour, but as you should have noticed, this is in 8 meters per second per second. It's always a good idea when you look at these problems to actually eliminate these things before you even start a problem. So the first thing I would have done with this is create a shopping list. Say I have 80 kilometers per hour, 8 meters per second, and I want t, and then I would have immediately converted this so I wouldn't have to do it later. I've left the conversion in just so you can see it explicitly. So we've got to take our 80 kilometers per hour, multiply it by 1,000 to get it in terms of kilometers, and divide it by 3,600 to get it into seconds, this being 60 minutes times 60 seconds to make up an hour. If we do this, we can then have 80 over 8, put the conversion through, we'll end up with about 2.78 seconds. Or, if you're going to round, make the first statement of 2.78 and then say this is approximately 2.8. So how far is the bike from the car when it reaches this speed? Well, first we want to know how far has the car gone. Then we can calculate how close the bike is. So for the car, its distance, s, is equal to v times t. This will be 80 kilometers per hour again, multiplied by the 2.78 we just calculated. Convert the kilometers per hour, and we should get 61.7 meters. Now, in the case of the bike, we need to know how far that has traveled. And what we can do here is say that s is equal to vt plus half at squared. Now, the initial velocity of the bike was 0. This means the VIT from s equals VIT plus half at squared is set to 0 and disappears, leaving us with s is 1/2 at. We know that the acceleration is 8 meters per second and the time is 2.78, giving us 30.7 meters. Now, is that the solution to this problem? Quite often people reach this point and stop. No. The question says, how far is the bike from the car when it reaches this speed? So what's the separation between these two vehicles? We're left with 61.7 meters traveled for the car, 30.7 for the bike. The difference is going to be 61.7 minus 30.7. So this answer was actually close. The final separation of the two will be about 31 meters. If the two of them carry on in this particular chase, the bike really shouldn't pass the car. Let's take a look at another example. A ferry boat moves with constant velocity of 8 meters per second for 60 seconds. It then shuts off its engines and coasts. Its coasting velocity is given by this function. V of x is equal to VIT squared over T2 squared, where T1 is 60 seconds. What's the displacement of the boat over the interval 0 to pretty much the rest of the time. Well, here's delta x1, here's our initial displacement, and here's our displacement after the boat's engines have shut off. So the situation is such that our graph will look like this. The velocity function for the boat is already given. So it's constant for the first 60 seconds. So delta x is just vi times t. That will be 8 times 60 seconds, which will give us 480 meters. The remaining displacement is going to come from an integral of the velocity graph, of the vt graph, from t equals t1 to essentially the end of our relationship. So delta x is going to be an integral of v dt. This will then be vix t squared with our limits from infinity to t1. This will come out, and we will integrate in terms of this 1 over t squared. That will give us this. Here's our limits. We'll end up with vit squared 1 over infinity minus 1 over t1, which, if we're to look at this, we can say this is essentially 0. This will be vi times t1, which will give us 8 times 60, which will give us 480 meters. That's a very complicated way of just essentially doing S is equal to VT, but I just wanted to run through the calculus of the situation just once. Now, that means the total displacement is essentially going to be delta x1 plus delta x2. It'll be 480 plus 480 and give us 960 meters. I would suggest you study this one in the PDF of these slides. Finally, let's look at another acceleration case. Here we have a car increasing speed from rest, so a VI of 0, to 100 kilometers per hour in 30 seconds. Find the distance the car has traveled over this time. So, as usual, what have we got? VI is 0, VT 100 kilometers per hour, TF is 30 seconds, and we'll assume it's under constant acceleration. That means A is dv by dt, or delta V by delta t. That's 100 kilometers per hour over 30 seconds. Once again, converting, 100 times 1,000 will take us to meters, 30 times 3,600, 60 times 60 here will take us into the second, essentially converting this into the same units in both seconds. This will give us 0.92 meters per second Our displacement, therefore, will be an integral of vt. So 0.92 t dt, our limits will be 0 to 30 seconds. This will be 0.92 t squared over 2 if we perform this integral. This will give us, after substitution, 0.92 times 30 over 2 squared, which will give us about 414 meters in 30 seconds. And that leads us to the end of our discussion of displacement, velocity, and acceleration. Please make sure that all assignments are completed by the deadline, and next time we'll talk about vectors.